Okay, so guys, today what we're going to do is we're going to take these half reactions and these oxidation reduction reactions that apparently you guys are good at balancing because we just sort of zip through grading homework, and we're actually going to do something practical with them, and we're going to talk about how it is that we can take these things and we can put them together and we can build batteries. So for those of you that are in my lab class, you've already had a little bit of exposure to this, largely from the book and casual conversation that sprung up during the class. But guys, today what we're going to do is we're going to formalize all of this. So the way this is going to go is we're going to start the day by talking about an oxidation reduction process generically. We're going to talk about half reactions. We're going to talk about what this might look like. And then we're going to visualize it by watching a video. Then guys, what we're going to do is we're going to take that same oxidation reduction process and we're going to magically reorganize it so we can turn it into a battery. What you're going to find is the chemistry doesn't change, the location changes. The organization changes. And at that moment, we're then going to watch another video that talks about how this thing can be leveraged as a battery. Then we'll bring up an image from the book and we'll talk about how a battery works and we'll talk about all the pieces and the parts. And then guys, at that point, I'm going to put this up on the wall and praying that my board works, we're going to actually label this thing and we're going to talk about all the dynamics that make a battery a battery. Then at that point, we're going to talk about voltage and how voltage can not only be understood but also calculated, and that'll be our day. You good to go? So that's what we're doing. So guys, it starts like this. We're going to start by going back to what we already know. So we understand, and you don't need to write this down, but guys, we understand that oxidation is the loss of electrons. We understand that in a half reaction then, electrons show up on the product side. But guys, this is an additional thought that will become more important in a minute. Many times, well, let me say it differently. When we think about batteries, because batteries are always made of metals, guys, when we think about batteries, when we think about oxidation, you need to picture metals losing electrons into solution. Oxidation is losing electrons, but guys, in the context of batteries, keep in mind that what you're going to see is metals, literally solid pieces of metal, losing electrons into solution as the metal goes into solution as an ion. Then the other side of this is reduction, which is a gaining of electrons. Here electrons appear on the reactant side of the equation. And guys, when we talk about batteries, what you're going to see is metal ions gaining electrons and being deposited as an elemental solid on a piece of metal that already exists. So what does this look like? Well guys, I wonder if you remember doing this last year. Do you remember this? What kind of reaction is this? Single displacement reaction, right? And guys, interestingly, my general chem kids are just turning in this lab, but that unit, when you learned reaction types, remember that was the one when you stuck the burning wood splint into the hydrogen and it popped and you almost wet your pants a little bit. It was like, and you giggled and might have, anyway. So yours didn't pop? You felt cheated. But guys, during that lab, one of the things that you did was took copper sulfate solution, which has that pretty blue hue to it, and you dropped in a piece of zinc, which is this chemistry. On the left, you've got solid zinc, and you've got aqueous copper 2 sulfate, the blue solution. And I wonder if you remember, you stood it up in your test tube rack, and then you came back to it after doing the last reaction, which was a precipitation. And then you came back to it, and do you remember what the zinc looked like by any chance? It was different colored. It was actually brown or rusty, or even, if you really could see it, it was copper colored. What you had actually done is copper plated the zinc. And guys, this was actually the single displacement reaction that described the chemistry, but now you can also look at this and you can say, not only was that single displacement, it was also oxidation reduction. And so guys, with that thought, why don't you do this? Write the net ionic equation for this reaction and then write the half reactions. And then guys, when you're done with that, answer this question. What substance is being oxidized and what substance is being reduced? Because while you're doing this, and I don't mean to be distracting, but I forgot to mention this in our introduction, but I told some of you that I would mention it. I think I've showed you pictures of the things that well, certainly Hunter and I have been talking because his uncle was going to help with part of this project. You know, we've been finishing up our church building, and some of you were like, hey, is it done? And I told you that I would tell you when we do our open house. That's actually tonight. So if any of you are interested in coming, it's from 5 to 8 o'clock. We're going to have a food truck rally, so Waffle Love and all of those people will be there. And what's that? I don't know. I'm not sure. I know Sweeto Burrito's going to be there, Waffle Love, and then the one that's got like barbecue. Anyway, so if you're interested in coming, it's from 5 to 8 tonight, and you can come see the cafe thing I built.
So the way you described it, I can tell if you're just telling maybe bands or restaurants.
It's all delicious. Yeah, so it's not on Geneva. It's down on Sand Hill Road. So if you go to the Walmart on Sand Hill Road down by UVU and keep going south, it's about 3 blocks south of there, on the freeway side of the road. Okay, so guys, let's not dwell on this too much because it's sort of not the point, but let's talk about it. So in order to do the net ionic equation, what does that by default mean we're getting rid of? The spectators. And so the spectator in this process is actually the sulfate. Now guys, as soon as we remove the sulfate from that, it requires that we know charges. Because we understand that these things are aqueous in solution, and in order for metals to be aqueous in solution, they have to be charged ions. So the net ionic equation then would be solid zinc. And by the way, guys, on the test and the AP test, you do not put subscripts on anything. You don't get points for doing it, and if you get them wrong, they're going to mark them wrong. So guys, do not put subscripts on things. So we understand that if it just says zinc, that's understood to be an elemental solid. But guys, what is it about copper 2 plus that tells us it's aqueous? The charge. Copper 2 plus is only, any metal ion is only stable in aqueous solution. So guys, the fact that it's copper 2 plus tells us that this is aqueous, and then our products are zinc 2 plus and copper. So that would be our net ionic equation. So then guys, if we wanted to do the half reactions, they would look like this. Elemental zinc is becoming zinc 2 plus, but in becoming zinc 2 plus, we understand that that's losing 2 electrons. We now understand that the electrons are on the product side, meaning that zinc has been oxidized. Then guys, our other reaction is this. Copper 2 plus grabs up those 2 electrons, and it becomes elemental copper, and that would then be our reduction. So guys, making sure, because remember I tricked you on this in September and some of you missed it, so let's be clear. What is the substance that is being oxidized? Zinc. What is the substance that's being reduced? Copper ion. Good. Now guys, the idea then is this. We actually you've seen this in the test tube, but guys, let me then maybe show you what this looks like at a molecular atomic level, not through simulation, but through animation. And guys, this process would actually look like this.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation.
So we've got the zinc metal. I don't know what's sloughing off of that. That was weird. But we've got the zinc metal, and we are in a copper ion solution.
Reduction reaction occurs.
So as we zoom in then, these are the zinc atoms. They are in their elemental form. Looking back at the half reactions, what's going to happen to this zinc? It's going to be oxidized and lose electrons. Where will those electrons go? Not to copper ion. And guys, where is the copper ion? It's in solution over on the right.
In this reaction, zinc is again oxidized. Now, however, copper 2 plus ion is reduced.
Okay, so now notice what happened. The copper 2 ion was reduced. What did it then become? Copper metal. And so now, guys, what's going to happen to the zinc ion now that it's lost its 2 electrons? It'll go into solution. It is no longer bound to the piece of metal, and it will go into solution.
To copper metal. In the 2 examples we have seen, zinc is oxidized because it causes...
Notice, guys, they're talking about 2 examples. This is actually a cropping of a larger video.
The reduction of other substances. Zinc is said to be a reducing agent. The substances that are reduced in these...
And the other one doesn't really pertain. I should just cut that out as well. Guys, the thing that we need to focus on then is the chemistry of the switching of electrons.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation-reduction reaction occurs. In this reaction, zinc is again oxidized. Now, however, copper 2 plus...
Okay, so I want to stop there for just a second. You guys, I think, are comfortable with this idea of the exchange of electrons, right? Zinc is oxidized, it's losing electrons through contact. Those electrons are being transferred to copper ion. The copper ion is then reduced to copper metal, and the zinc metal is oxidized to copper or to zinc ion. You get the idea? Okay, but guys, what does that entire process require? And the answer is this exchange of electrons. You okay with the idea? Because, guys, this is, no pun intended, the bridge to a battery. Okay? Because here's the idea. We understand that when we get copper and zinc together, copper ion naturally wants to take in electrons. Zinc naturally wants to give away electrons to copper ion. We're going to find out in a few minutes that we can explain that using this table. Why is it that zinc gives away electrons, and why is it that copper ion takes them in? And guys, it has to do with electronegativity, it has to do with size, it has to do with electron affinity. But guys, it can all be summarized in this table. So if you're looking at zinc and copper and you want to know who's going to give away electrons and who's going to take them in, you're going to find out those answers are contained in this table. We'll get to that later. For now, we just understand that zinc is going to be the electron giver and copper ion is going to be the electron taker-inner. The question is this: how do we make this then into a battery? Because this is a really good battery. It's more than a volt. How do we do it? What do we have to do to turn this into a battery? Exactly. Exactly, you got to separate them. See, guys, copper and zinc are going to exchange electrons. If you bring them into contact, it will happen through contact. But if you can separate them and then connect those two with a wire, they will still exchange electrons, but you can force the electron exchange to not happen through contact, but to happen through a wire. And if the electron exchange happens through a wire, we now have what we call current, and that is a battery. Because, guys, electrical current is just the flow of electrons. And if we can trick these two guys into doing what they naturally do and exchange electrons, but do it in such a way that we can force those electrons through a wire, we now have a battery. You get the idea? Does that link make sense? So guys, let's now take this same reaction, and instead of thinking of it strictly as an oxidation reduction, let's now put it in the context of being a battery. Oh gosh, sorry, I clicked on the wrong thing. So we're going to take this then, and actually let me give you lights out. We're going to take this same reaction then, and we're going to cast it now in the understanding of a battery. So look at where we're starting. What's the metal? Zinc. What's the solution? But I believe in this one it's not copper sulfate. I think the example is copper nitrate, but why doesn't it matter? It's a spectator. So regardless, let's pull the pieces together.
When a strip of zinc metal is immersed in an aqueous copper-2 sulfate solution,
This is sulfate, okay.
electrons are transferred from zinc to the copper-2 ions.
And we saw that, right? We saw it in the animation. We saw it in the balanced equation. And now, remember this? That's what it looked like in your test tube last year, right? What's the brown fuzzy stuff? The copper. But let me ask you this question, and you weren't in a position to answer this last year. You notice if you do before and after that the copper is deposited on the zinc. But do any of you notice the other subtle change? The solution color. On the left, it's bright blue. On the right, it's still blue, but less blue. Why would that be the case? It's not because of the zinc going into solution. Less copper ion. Guys, and this is something you need to know on the AP test. Copper ion solution is blue. And so look at what's happening. Over here, we have a bunch of copper ion floating around in solution, but as this oxidation reduction takes place, the copper ion is being converted into copper metal. Is that oxidation or reduction? Think about it, guys. Copper ion, lots of it on the left, right? Left, right. And on the right, there's less copper ion because the copper has become a solid. So copper ion is becoming copper solid. Is that oxidation or reduction? Reduction. So guys, remember what I said on the very first slide. When you think about batteries, when we think reduction, which is gaining of electrons, it's ions being deposited as a solid. So let me tell you how I envision this. I think of ions as floating around and they come down to their solid form. They're reduced, they're brought down, they're reduced to their solid form. And it's always like that because metal can only be a positive ion. So if it's becoming its element, it's being brought down in charge to its solid form. So guys, this copper ion, which is blue in solution, is being reduced to copper metal. You get the idea? Okay, so now let's turn this into a battery. I'll play this twice.
Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc-2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a Voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper-2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a Voltaic cell, the anode at which oxidation occurs is the negative electrode, The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
Tons of material, right? Guys, this is one of the few videos that comes bundled with our book where they do a summary. There's tons of details. And guys, the details are not here. The details are here. We need to talk about and help you get your arms around all of the details that are represented in this still of the video. So let me sort of tee this ball up for you so that you understand what it is you're eventually going to have to get your arms around. So guys, the first thing that you've got to be able to think through is the chemistry that is happening in both of these cells. You've got to understand that at the anode, oxidation is occurring. As oxidation occurs, the metal anode, in this case zinc, is being oxidized to zinc ion. And you need to understand that as the zinc goes into solution, electrons are being released, which then go through the external circuit that we understand to then be voltage. Other things that you've got to keep track of that they didn't mention in the video is what is happening to the concentration of the solution and what is happening to the mass of the anode. And we'll talk about that more in a minute. Then guys, similarly, you've got to have the same ideas nailed down about the cathode, where reduction is taking place as the copper ion is reduced to copper metal as the electrons are taken up that were originally released by the zinc. In addition to that, you've also got to be able to understand what is going on inside the salt bridge, including why is it they chose sodium sulfate as the salt in the salt bridge, and what is a salt bridge, and what direction do the ions in the salt bridge flow. And then in addition to that, guys, you've got to be able to figure out how they came up with the voltage, which in this case is 1.10 volts. But that's all. Did you notice though how that just sort of flowed off my lips? It's almost as if I've done this before. So, guys, what I'd like to do is I'd like you to have the experience of seeing this a second time. Then what we're going to do is we are going to take the ideas, not expecting all of you to remember all of it, but expecting at least one of you to remember a piece of it. We're going to piece this all together, and we're going to do it on here. And we're going to have these conversations about what's going on here, what's going on there, where electron, what's happening to concentration, what happened to mass, where did 1.1. We're going to do all of that on here. So what I want to do, guys, is I want to give you another shot at this video, and then we will summarize and distill together on this sheet of paper. So let's do this one more time. We'll sort of start back here. No, we won't.
Atoms are This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a Voltaic cell.
Were any of you surprised that the compartments don't contain the same solution? Okay.
The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
All right, you ready to pull this together? Here we go. Is your spacing, so guys, you have a little bit more room beneath your cells than I do. So I don't know, you're going to have to sort of, well, here, no, let me do this. There isn't a lot that needs to be written above, so let me sort of just push this up a little bit. That'll give me similarly more space. It looks awkward, but it'll work better. Okay, so guys, I would suggest that fundamentally, foundationally, let's try to make this as much like the video. So in doing that, I would suggest that it's probably wise to keep zinc on the left and to keep copper on the right. Now in doing that, are we all comfortable with just not even mentioning the spectator? Well, you know what? Let's mention the spectator. The reason being because it influences what we put in the salt bridge. So let's do this. You know what? Let's just do this. Let's have the conversation now, and then we just won't write it down. So this is zinc. Come on. This is zinc 2+ solution. This is copper 2+ solution. But we understand, guys, that these are both salts of sulfate. So now let's talk about, we're not going to talk about what the salt bridge does, but let's just establish what our salt bridge will be made of. So guys, our salt bridge will be made, our salt bridge will be made of sulfate and then let's just say it right now, and I'm not going to balance it, it's Na2SO4 of course because of charges. But guys, why would we choose the sodium of sulfate? Well, it's soluble and it's neutral. It doesn't do chemistry, right? Sodium loves to be a spectator. It's not reactive towards water as a conjugate acid because it's the child of the weak or the strong base, sodium hydroxide. So when you're picking your salt for your salt bridge, what you'll do is your anion will be whatever the anion is in the two cells, and then your cation, just pick sodium. You could pick any of the group 1 or heavy group 2 metals. Sodium's always a safe bet. We'll talk more about the salt bridge in a minute, but this allows us to not include the sodium, or include the sulfate, I mean. Okay, so now guys, let's talk about the chemistry that's taking place by representing the half reactions. So let's focus on our zinc cell first. So guys, what is taking place in that cell? Is zinc metal becoming zinc ion, or is zinc ion becoming zinc metal? Metal to ion? Yes. So zinc is becoming zinc ion, and it is releasing 2 electrons. Now, how do we know? Because the video showed us. What if we didn't have the video? We'll talk about it in a minute when we grab our reduction potential charts. And then guys, similarly over here, or maybe inversely, copper ion is grabbing up electrons and it's becoming copper metal. Again, how do we know? Because we saw it in the video, but we'll talk more about how we really know in a minute. Okay, so guys, this is the chemistry that's taking place. So at this point, it's going to be helpful to draw some arrows. So given that zinc metal is becoming zinc ion, guys, I find it useful to do this, just to show me movement. So during this process, zinc metal is moving into ionized solution. And then conversely, copper ion is being deposited, reduced to copper metal. So guys, it's at this point, and be careful, you've got more space than me, you're okay. But guys, let's now talk about those two interesting questions about concentration and mass. Look at our left-hand cell, and let's just call it what it is. Is that oxidation or reduction? Oxidation. How do we know? Electrons are being lost. By whom? Zinc. So guys, in this oxidation cell, let's talk about mass and concentration. What is happening to the mass of the zinc? And this is called an electrode. The piece of metal is called an electrode. What is happening to the zinc electrode? Is its mass going up or down? Down. It's literally atoms of zinc are going into solution. So here, guys, I'm just going to write it over here. Mass is going down. And is that enough that you understand we're saying the mass of the electrode? But now, guys, what about the concentration of the solution? What is happening to the concentration of zinc ion in solution? It's going up. So increasing zinc ion concentration. You good there? So now let's have the same conversation over here. And I know the answer is obvious, but what's happening in the copper cell? Reduction. It's the opposite. So guys, now let's talk about the changes. What is happening to the mass of this piece of copper? It's increasing. So writing this similarly, we then have an increase in mass. And guys, interestingly, on the AP test 2 years ago, when they asked this question, they didn't tell you which one was the oxidation or which one was the reduction, and we didn't have a reduction potential chart. But they did tell you that the mass of the electrode in the left-hand compartment was going up. And they expected students to be able to pull together the idea that that would then be the place where reduction's taking place. So guys, the mass of this is going up. Where's the copper coming from? The solution. And therefore, what's happening to the concentration of the copper ion? It's going down. So decreasing concentration of copper ion solution. Okay, so now guys, let's lend names to these things. We've already said it, but let's formalize it. So the thought here then being, let's go back to our left-hand cell. Our left-hand cell is the zinc cell. The zinc atom is losing electrons. What did you tell me that process was? Oxidation. So we're going to say that this cell is oxidation, and that has a name. I don't want to draw an arrow because you're going to think it's another reaction. I'll put it in parentheses. Come on, baby. Come on. There you go. That process always happens at what we call the anode. And then, guys, similarly, over here on the right, we have reduction, and that is called the cathode. Now, guys, you've got to know that. How are you going to keep straight that reduction is at the cathode and oxidation is at the anode? The easiest thing I've come up with is vowels and consonants. Vowels and consonants. It works for me. Anode, oxidation, cathode, reduction, vowels and consonants. Can we keep those together? Okay. So now that we've talked about the chemistry that's going on in these cells, let's talk about the batteryness of this. And guys, what we're going to do is we're going to talk about the salt bridge last. So let's talk about how this then functions as a battery. So guys, this right here does not fully describe the chemistry. Yes, zinc is becoming zinc ion, but when zinc becomes zinc ion, the electrons are coming off. We describe it in the half reaction, but we haven't described it in the picture. So the other thing that we end up with is 2 electrons. And where do those electrons go? Well, they're looking for a place where they're wanted. They are not wanted in the zinc compartment. Zinc is going, I don't want you. But guess what? There's somebody over here that's going, I'd love to have you. Who over here in the right-hand compartment would really love some electrons? Copper ion. So what happens then is these electrons travel through this external circuit. They coat the copper electron, the copper electrode. So this then has an abundance of electrons, and that copper ion goes, hey guys, look, electrons, let's go get some. And the copper ions are drawn to the copper electrode because of those excess electrons. The copper ions come over, grab a hold of those electrons, and in doing so are reduced to copper metal. So guys, summary then, which direction do the electrons flow? Well, they flow in this direction. Current always flows from anode to cathode. So now, guys, let's associate all of these thoughts. Good heavens. Let's associate all these thoughts with a battery. So, guys, this is exactly what's going on inside of our little Duracell here. And you'll notice that we've got a positive end, and you'll notice that we've got the negative end, which is the bottom of the battery. And similarly, because this is a battery, just like this is a battery, these things have a positive and a negative end. So which is which? Is the anode the negative or the positive end? Well, the anode is actually the negative side. Because remember, over here we've got an abundance of free electrons. That makes this side negative, and it makes this side positive. Now, guys, surprisingly, what does that mean in terms of current flow? Current flow always goes from negative to positive. But doesn't that make sense because electrons are negative and we've got a greater number of electrons on the negative side than we do the positive side? And so just like things flowing downhill, like water flowing downhill, if we've got more electrons over here than we do over here, the electrons flow from the negative anode to the positive cathode. So current flows from negative to positive. Yeah. I don't even know what that is. So I'm assuming, let's don't. I don't. We can talk about it later, but this is a scary point and I don't want to confuse things. So I don't know. So guys, we okay with anode, cathode, oxidation, reduction? Let's call time out because the only thing we haven't talked about right now is the salt bridge. So are you okay with the chemistry that underlies all of this but the salt bridge? Yeah. No, it's not a limiting rate. So we're going to talk about this for an entire day, but let's sort of tee the ball up now. When do batteries die? And the answer is not when they run out. It's when they reach equilibrium. Because what happens, and we're going to talk about this more later, we have two competing processes going on here. We've got more electrons over here than we have electrons over here. Did you guys hear Gavin's question? When do batteries die? And so the idea is this. We have what's called a gradient, in the same way that a hill, you're driving your car down a hill and it's got a gradient and your car wants to go downhill. You have a gradient, and we've got a charge gradient. We've got a greater potential of electrons on the left than we do the right, and those electrons flow downhill. We also have a concentration gradient. What we're going to talk about is that as this cell does its thing, the concentration of this solution is going up and the concentration of this solution is going down. And when the concentration gradient and the voltage gradient offset each other, the battery dies. And so that's what's happening. As the electrons flow in this direction, these are closing in on each other. There's fewer electrons here, there's more electrons here, and these close in on each other. But the opposite is happening as well. This concentration is going down and this concentration is going up, and eventually they cancel each other out and the battery is dead. We can reset it though, right? We can hook this up to a battery charger. Rather than having like a light bulb or something here that we light up, if we replace that with a battery charger, it drives the reaction in the other direction, resetting the gradients, and then the battery is ready to go. So why aren't all batteries rechargeable? I don't know. So go ahead, Joey, just a second. Go ahead.
So we learned that
Right, right. And I don't know why. So guys, let me give you my little plug right now. Okay, you ready? If you want to change the world, and if you want to earn more money than you will ever know what to do with, although one of the things that you should do with it is give some to me, because I planted the idea with you, and I originally taught you about batteries. So when you become filthy rich, help out a brother. Guys, seriously, if you want to change the world, invest your life in building batteries. We could totally change the political, the economic, the environmental scenery of this world if we could just build good batteries. We totally have the ability to generate enough clean electricity to get us completely off of fossil fuel forever. The problem is the wind doesn't always blow and the sun doesn't always shine, and we don't have a way to store it. You guys understand that, right? So when we figure out how to take wind and solar and hydro and all these other sources of electricity, and when we can put those in a battery and hang on to them and then use them anytime we need access to this power, done. It's just like that. Because interestingly, the people right now that are doing the most innovative work in this stuff is Tesla. Are you familiar with the company Tesla? This is crazy. When Tesla originally started building cars, the best batteries available on the market were in cell phones. And they actually took thousands of cell phone batteries, soldered them together, and used those initially to drive their cars. Then they realized, hey, we need to do a better job of building batteries. So Tesla is now they have their own battery department, and they build batteries for cars, and they're getting really good at it. They're actually now building cars that have cruising ranges only on electricity for hundreds of miles. So have you seen what they've done? They're actually now taking the batteries that are in their cars, turning them into artwork, and selling them to hang in your house. Have you seen these batteries? They're beautiful. They're very, look them up. We're thinking, my wife and I are thinking about buying one and going solar. They're pretty. They have like illumination. You could easily put it in your living room and it wouldn't look out of place. It's all sculpted and it's really kind of attractive. But you wire it into your home electrical system, and whether you do solar or not, you can wire it straight into the same power that feeds your home right now, and it's always charging. And when the power goes off, it switches on and it powers your entire home. These guys and they're only like $2,000. It's unbelievable. Because if you want, I'll show you this video when we're done with the AP test. It's the place, do this, and then we can show it to you later. Look up on TED liquid metal batteries. They are actually now figuring out how to make grids. It's called grid level storage. You understand there's the electrical grid, and for us to get off of fossil fuels, we've got to be able to store the same amount of electricity that exists on the grid. And this guy at MIT, who's amazingly pretentious, actually has figured out grid-level storage. He's taking semi-trucks, the trailers from semi-trucks, and turning them into batteries. It's fascinating. Look it up. They're called liquid metal batteries. Look them up. It's pretty cool. So anyway, you guys good on this stuff? So you're going to go build batteries, right? And then share with me? Not your battery. I don't want your battery. I want your money. All right. Yeah. Again, I don't know. I know I can teach you the fundamentals of batteries, but the people that are really doing this fascinating cutting edge stuff, I mean, they've invested their life. Why is it that the batteries that we're going to build in lab, and unfortunately you won't be with us, they die arithmetically. They have a starting voltage and their voltage tapers off down to 0 when the battery dies. That would not work in your cell phone, right? Because your cell phone needs to have a constant voltage in order to work. So the battery that's in your cell phone, if you track the voltage of it, the voltage over time, so voltage in time, the batteries we build die like this. Cell phone batteries die like this. They maintain their voltage to feed your phone, and then they plummet. That's why your phone all of a sudden shuts off. It doesn't get dim, it just works, and then it doesn't. How do they do that? I have no idea. It's fascinating. I love it. Yeah, it's really cool, but I have no idea. So, guys, let's talk about salt bridge. For those of you that understand the fundamentals of batteries or circuits in general, you understand that if you don't have a complete circuit, things don't work. So that's what the salt bridge does. It completes the circuit. So what does this look like? Well, guys, draw this in with me, and I'm going to make this red so it stands out. So a salt bridge has got a cap on either end. This cap is what is called a semi-permeable membrane. What does that mean? It means some things get through and other things don't. So what gets through? Ions. What doesn't get through? Water. So guys, the way that this works is you charge the salt bridge with a salt solution. And what that salt solution does is it allows the charge to balance and it allows the current to flow. Now what you've got to be able to figure out is what direction do these ions flow. And so guys, you can think about this in multiple different ways. This is the way that I like to think about it. So we've got negative things flowing this way, right? Literally right. Electrons right. So if we've got electrons, negative things flowing this way, the negative things need to continue to flow this way in order to continue to go. So the negative thing will flow this way. And then similarly, the positive thing, the sodium, will flow this way. But now you're saying to yourself, wait a minute, that doesn't make sense because I've got a negative thing being attracted to a negative thing. See what I'm saying? Does that make sense? But guys, you got to understand that's so it's not that this negative thing is being attracted to this negative thing. That's not what we're saying. We're saying that, well, or maybe you could think about it this way. If you like the idea of attraction, let's talk about where the attraction lies. This negative tells us where the electrons are going. But look what's happening to the solution. The solution is becoming more positive, right? Ions are going into solution. That's why the negative is attracted in this direction to neutralize, if you will, the solution. So maybe that's a good way to think about it. As more zinc ion is being formed, the negative sulfate ion comes over to neutralize the solution. And then similarly here, as copper ion is being deposited, this solution is becoming less positive, so these positives go that way to maintain a charge balance. Is that okay? So if you want to think about the cycle of life, if you will, negatives are going this way, and the negatives just keep going this way, which would explain the negatives doing that. Or if you like the idea of attractions, the idea is focus on the solution. So guys, now we've got it. Those are all the pieces and parts and bits and concepts and terms and realities that circle around a battery. So clarification, questions, things you all want to explore. And then guys, just to tee the ball up, we're going to spend the last 10 minutes and we're going to talk about voltage and figuring out the voltages of these batteries. So let's just go backwards. Spencer's been waiting for a minute. Go ahead.
How on earth do they make a membrane? It's like I know in biology they have
Yeah.
like those membranes, but I feel like those are just sort of a lot of. I feel like those would eventually just dissolve because they've got lots of weird.
Yeah, so there's a couple answers to the question. One of them's interesting and the other one's disappointing. So let's make sure everybody knows. So Spencer's talking about these membranes right here that cap the salt bridge. A great membrane for that is actually Gore-Tex. If you're familiar with Gore-Tex, which they make high-performance clothing out of, what they do with Gore-Tex is they actually take a piece of something that sort of resembles Teflon, and when they stretch it, a bunch of little holes pop into it. This guy made a lot of money figuring that out. But it turns out that these holes are actually bigger than steam, but smaller than water droplets. And so the idea is all of these little bitty holes allow sweat to go through, but they don't allow raindrops to come in. So it's semi-permeable. That's how Gore-Tex works. Those same size holes actually work with ions. Water is bigger. They stretch it so the holes are different, but you can stretch things like that such that the holes are big enough that ions can get through, but they're small enough that water can't pass through it. So, but with that said, you're going to find out in lab, when we go do this lab on Thursday, the thing that we're going to use as our salt bridge is actually string. Yeah, because string works too. You can actually bleed some of the water through this and it actually replaces itself. So it's not horrible if water does transfer because there's water in both cells and it all sort of works out in the end. So those don't have to be semi-permeable. It can actually, the thing that you can't have is you can't have a direct flow because then these start coming into contact with each other. You need something that either doesn't flow at all or flows slowly enough that it doesn't allow these two solutions to mix. And string works.
I'm making an electrolytic cell and it's just always messed up. And I'm like, what's going on?
Yeah, and that could be it. So, Josh.
My question is the salt bridge like a solution inside of like a tube?
It is. Absolutely, yes. This is sodium sulfate dissolved in water trapped in a tube. Or it could be a string dipped in sodium sulfate solution. Yep. Anywhere else? I'm going to give you 2 minutes and then we're going to go regardless of where we are. Go ahead, Liz. No, it is not electrons. It's ions. It's the sodiums and the sulfates. Yeah, there is not a, if there were a current of electrons going through here, we'd have no battery. Because the battery would take the path of least resistance, and if the electrons could transfer through here, they would, and then we wouldn't get a voltage in the wire. Yeah. It could be. I mean, for us, yes. Technically, no. I mean, you could have nitrate in your salt bridge. No, so long as whatever's in here doesn't react with whatever's in there, you're groovy. Yeah, go ahead.
So does each solution have to be like electrically neutral, or you could have the same concentration of negative charge?
No, not at all. No.
Does that mean that why do you need the salt bridge?
Well, because even if these ions didn't have the same charge, we would still have a changing charge. Even if this was like +1, this would still be becoming more positive as more of the ions are oxidized as more of the atoms are oxidized into solution. And it's the change in charge that we're trying to account for, and therefore we need the movement of ions.
So, like initially, if you didn't have a salt bridge,
There'd be no current. It wouldn't flow. You'd have no battery. Okay, so guys, let's do this then. Let's now answer the last question about why does, remember in the video it produced 1.10 volts. So let's now have the conversation. Why does the voltage flow in this direction to begin with? Why does it go zinc to copper and not copper to zinc? And then how do we know that that voltage is 1.10 volts other than building it and putting a voltmeter on it? And guys, in order to do this, you need this. So grab your reduction potential chart. And guys, the first thing that you need to be sure about is this is a reduction potential chart. These are all written as reductions, and we know that because they're all written plus electrons. Okay? Now guys, a couple brief observations before we really dig into this. First of all, these are all written as reductions, right? But we understand that you can't have reduction without oxidation. So the only way to figure out reduction potentials is by building these batteries and figuring out what they do, because you can't have reduction without something being oxidized to lose the electrons that can then be added and cause the reduction. So all of that means we've got to have a 0 point. We've got to have a standard. And if you look on the table, what's the 0 point? It's hydrogen. It doesn't matter what your 0 point is, but we just choose hydrogen as our 0 point. So positive voltages then mean that the substance that's on the left, in the case of the very top one, fluoride, F2, is better reduced than hydrogen. And then anything beneath hydrogen is not as well reduced, as readily reduced as hydrogen, so it's all relative. But guys, if these things are all relative, those relativities extrapolate even if we don't relate them back to hydrogen. So what that means is if we look at fluorine and then look directly, do you see where I'm saying fluorine at the very top? That's why I'm going there. So if you look at fluorine and then directly beneath that at cobalt 3+ ion, guys, what we now know is this. Fluorine is more readily reduced than cobalt 3+ ion. How do we know? Because fluorine's above it. And then we could compare the voltages to figure out how much better it is at being reduced. So these relationships travel throughout the entire chart. So with that said, find our two players in the battery that we have up on the board. And guys, if you need another copy of this, I'm happy to share it out with you. I'm actually going to circle them because it makes them easier to find. So let's find zinc. And you'll notice that you find zinc with a negative voltage. Zinc 2+ plus 2 electrons yields zinc solid negative 0.76 volts. And then guys, you'll notice that you've got 3 examples for copper, right? Which one are we talking about? Top, middle, or bottom? Middle. So if you want to circle that one too, that's not a bad idea. Okay, so now let's answer this question. And I'm using left and right, only specific to what's on the board. Why does this battery flow from left to right? Why does it flow from zinc to copper? Well, guys, let's think about this. You ready? This is a reduction potential chart. So this is telling us the potential with which these things are reduced. Does that make sense? So, which substance is more likely reduced? Copper ion or zinc ion? Copper ion. How do you know? Because it's above it. What's that? But even if they were both positive or both negative, we can still build batteries that way. They're not very good batteries because they're fighting against each other. But it's not just because it's positive, it's more positive. Okay? So guys, bottom line is this. Whoever's higher up on this chart will be the cathode. Because what happens at the cathode? Constant. What happens at the cathode?
reduction. And so if this is a reduction potential table, whoever is at the top will be the better reduction thingy, which will make a reduction. And because copper is higher, that makes it that copper is the reduction. That's the place where reduction happens. Do you now understand how to identify the cathode based upon the fact that the cathode contains reduction? Is that okay? Okay. Now, guys, with that said, let's then figure out where this voltage 1.10 volts comes from. So, guys, take a look at this. Is that half reaction written the way it's written on this table? It is. And what is the voltage of that process? Positive 0.76 volts. Now, guys, let's talk about... Oh, did I do the wrong one? Oh, thank you. Sorry. Thank you. Plus 0.34 volts. So, guys, let's now talk about what is voltage. And all of this is represented in the notes that we're not going to look at. But, guys, think about it this way. In order to understand current, think about a garden hose. Okay? And if you've got a garden hose with water flowing out of it, there are two important characteristics of that stream of water: pressure and flow rate in gallons per minute. So if you've got water coming out of a hose, so pressure, right? Is it coming out as a trickle or is it like a laser beam, right? Pressure. But then also flow rate, how much water is coming out. Guys, you can have a very high pressure flow of water, like, but there's not much water behind it, right? That's kind of how pressure washers clean your car. That's why car washes work, because they don't move a lot of water, but the water they do move is at a very high pressure. But then, guys, you can have the other end where you can have a flow of water that's just gushing like crazy, but it's barely going anywhere because it's very low pressure but high volume. You know what I'm saying? So, guys, similarly to that, electricity functions the same way. Pressure is voltage. So pressure in a water line is similar to voltage in an electrical current. And so we have high voltage, which means there's a lot of force pushing those electrons through the wire. But then we can also talk about flow rate. And guys, flow rate in electricity is what we call amperage. So the number of electrons that are flowing through there is what we call amperage. Do you see the distinction between the two? So voltage. Guys, what is voltage? Voltage is the pressure in the line. So let's talk about how this works. So guys, what does this mean that this has a voltage of 0.34 volts? Well, guys, what that means is this. These electrons right here are being sucked. They're being sucked into that cell with a pressure of 0.34 volts. How do we know that those 0.34 volts are a sucking pressure? Because it's positive, but what about this table makes it sucking? It's a reduction potential. Reduction is sucking in electrons. So if you have a positive voltage, that means you're an electron sucker-inner with a voltage of 0.34 sucking units, which we call voltage. Now, guys, let's go over here and talk about zinc. Guys, what's going on with zinc? Well, this is what's going on with zinc. But what is the voltage of that process? Negative 0.76 volts. So guys, let's talk about it conceptually and then mathematically. What does it mean that the voltage is negative? It's not a sucker, it's a spit. Literally. Guys, what zinc is doing is zinc is going, and well, I should go the other way. So zinc is going like this. Zinc is going, and it's spitting electrons into the wire. And copper ion is over here going and sucking them down the wire. Seriously, guys, this is how this works. Zinc atom inherently spits electrons, and copper ion inherently sucks in electrons. But do you notice that they're working together? This is a spitter with spitting pressure of 0.76 volts. This is a sucker inner with sucking inner pressure of 0.34 volts. So this is pushing, this is pulling, and as they work together, what do we do with those pressures? We add them together. So this is spitting with 0.76, this is sucking with 0.34. You add those up and you get 1.10. And that's where the voltage comes from. But now guys, here's the question. What if you just have the numbers and you need to deal with the numbers as they stand, and you don't want to go through the spitting sucking analogy because you're going to look like an idiot during the test? Here's what you do. Guys, grab your papers and let's make sure you're clear on this. Because the bell's going to ring. You all now have eyes. Okay. So, guys, if you look over here in this cell, is this half reaction written the way it should be? Let me say that differently. Is this half reaction written like this? Yes. Now look at this half reaction. The half reaction for the zinc is what is on the board the same as what's on the paper? No, they're opposites, aren't they? So what do we need to do? Well, what we need to do is we need to flip the arrow over, which means we flip the sign. Like that. Now we can add them together. Not yet. Now we can add them together. But guys, here's the trick. You ready for the deep thought? You are always going to flip the sign at the anode. Why will you always flip the sign at the anode? Because these are reductions, and that's not what happens at the anode. You get the idea? So what are we then going to do to create a unified equation that we can always apply? And the answer, thanks Jessica, the answer then is this. What we're going to do, guys, and understand what we're saying, the cathode stands as written, the anode needs to be changed. So guys, I want to make sure I get this the same as it is on the AP test, or on the AP chart. Guys, what we're going to do then is we are going to utilize this equation that you need to write down with me. It goes like this. The E of the cell, the voltage, the electrical potential, the voltage of the cell is equal to this, E naught reduction. So let's talk about what that means. That is the reduction potential. We write reduction because that's the reduction potential. Naught simply means 1 molar solutions at 25 Celsius. But guys, that is the E naught of the cathode. And then we subtract from that the E naught reduction at the anode. And why do we subtract the anode? What does the subtraction do? Changes the sign. You get the idea? So guys, this is what you're going to encounter in homework today. We covered a ton of material. I frankly have no idea upon which grades to base Pride. So here's your homework. Right there. And we're good to go.